Hello everyone, welcome to Physics CQ-METANS. This is the sixth video lecture on vector analysis. So in this video, we will discuss about the directional derivative and gradient. This is important, so let us see. Before we dive into this concept of directional derivative and the gradient, first let us see what we have discussed earlier. So we have talked about some fields. So one was the scalar field, and one was the vector field. Now, in order to study, now we know what is a scalar field and what is a vector field. So we have given certain examples of it. So scalar field is, suppose if I have a scalar field as temperature. So what is the temperature in a room at different points is what a scalar field is, for example. And now we will discuss about some operation with the scalar field. Now something, if I do some differentiation or something on a scalar field, so we will see that we will call it as gradient. And with vector we have something called as this divergence and curl. So we will see this in the consecutive lectures. Today we will be discussing about this gradient only. So now what is the directional derivative? So now first let us consider a scalar field. See, I have a temperature field that is given by T x y z at every point in a room. So that is what a scalar field is. So starting from a given point, suppose if I have a point over here, say this is the point 1, and I have some another point. So we want to ask what is the change in temperature as we move along the point. Say if this is the point, say this, we can call it as some point of or the reference point, and we want to see what is the temperature at different points as we move away from this point. So now what can be the possibility if I go from this point to any other point, say this point or this point? So the possibility is either the temperature will increase or the temperature will decrease. So how the temperature change will be shown, that is what we will see. So that is what we have written. The possibilities are that the temperature increases in some direction or decreases in some other directions. So the rate of temperature with distance. Now we are going from this point to this point. So as the distance changes, the temperature might change. So suppose if I have a rod, say this is a rod, and I am hitting this rod from here. So I can say, I can ask that what is the temperature over here and what is the temperature if I move away from it. Is it same or different? So that we can ask. So if it is heated over here, we know that it is a hot region, and if we measure the temperature at this end, it will be somewhat less, and at different points the temperature will vary. And if we heat it for a long time, then it becomes constant. That is, we are not going into the thermodynamics as of now. So the rate of change of temperature with distance depends on the direction. So in which direction I am moving. So from this point, if I move towards this point, so how the temperature varies. So this depends on the direction, in which direction I am going. So such change of temperature with distance is called as the directional derivative, and we will call this as delta t by delta s, where s is the some distance element and delta t is the change in the temperature. Now we write the directional derivative as ds dt by ds. Now what is the direction? So this we can ask a question that what is the direction in which dt by ds has its largest value. So now this physically, what this means is it is the direction in which the heat flows. Now we we can see Like I can take the points, different points, but I know that physically if I take some hot object and a cold object which is connected with some they are connected thermally, they are in thermal contact, so I always know that the heat will flow from a region of high temperature to a region of low temperature. So that is, the heat flows from a hot body to a cold body. So this is a direction. So the direction is from region of hot to region of cold. Now let us consider another example. Now if we consider a hill. So now we are standing at some point. Now I want to ask which is the steepest slope of the hill. So now this hill more or less looks very symmetric, but we know that the hills are somewhat like this. So we want to ask what is the slope, the most steepest slope. So one would say that if I lose my footing, the direction in which we will slide, I might slide, will be the most steepest one. So means I will unable to control and eventually I will fall down. So now in this case what changes is the vertical height. So as I fall down, so this vertical height changes. So where this vertical height changes has the highest value, that is the directional derivative. So that is the direction of the most steepest slope. So I can write dz by ds, where again ds is some length element. So from this, we also know that the potential is given by mgz. So we can also ask how can I maximize the energy? So we know that if I want to find, if I maximize this z, so where dz by ds is maximum, so v maximum will be like if I take the directional derivative of it. Now gradient has a very good physical implication that we will see. But let us proceed now. Now let us see one general case. Now we have given some few examples. Now let us generalize the problem of directional derivative. Now let's say we are at some point. See, we have a scalar field. So we are considering a scalar field. So which is a function of phi x y z. Now what we want to find out is the directional derivative, that is d phi by ds. So that is the rate of change of this scalar field with distance, how this scalar field is changing with distance. So now let us consider this point and let us call it as x naught, y naught, z naught. And we are moving along this point, this path to reach some point which is x, y and z. Now we know the distance. The distance between these 2 points is like s. S is the distance. So if I do x minus x naught, y minus y naught, so I can write it as s is equal to some x minus x naught, then plus y minus y naught and etc. But now along this direction there should be an unit vector. So let us call an unit vector u. So where u is the unit vector. Now this u, we will write it as some scale factor times I cap plus some scalar times j cap plus some scalar time k cap, where a, b, c and are some scalar in this given direction along this line. So from this figure what I can write is, so this us I can write it as x minus x naught. So this is the coordinate form. So this is x, y, z. It's the final coordinates minus the initial coordinates that will give me the this length of this vector. So now u is u, I'm just writing the value of, putting the value of u, that is ai cap plus bj cap plus ck cap times the s. So this I can write it as So if I write it component wise, so it is x minus x naught. So if I just open up this, it will become I cap plus y minus y naught j cap plus z minus z naught k cap, and that should be equal to ai cap plus b j cap plus c k cap. Now just if I compare the coefficients, so here I cap, so ith component will be x minus x naught is equal to, and this multiplied by s, sorry, so I will get it as as. So if I rearrange, I will get this equation. Similarly, if I follow the same procedure to for the jth and the kth component, I will get these equations. Now if you see, these equations are a equation of a line, the parametric equations, we remember. So these are the parametric equation, and this is an equation of line. So we know that if I differentiate this with respect to s, so we are no longer, so I will get basically then dx by ds is equal to a. So if I put this value of x, y and z in this equation of phi, so this phi is no longer dependent on x, y and z. It is just depending on the distance, that is s. So similarly, if we just put this value of x, y and z in this equation, you will find that we will just get the dependence on s. So that is what we have written over here. So these are the parametric equation of line through x naught, y naught, z naught. In the direction of u, the parameter is s, which is the distance. So if we substitute this x, y, z, which we found out in this phi, then phi becomes just a function of one variable, that is s. So as phi depends only on s, so what we can do is we can just find out d phi by ds. Now phi is a function of x, y and z. So if I do this, I will get dabba phi, sorry, dabba phi by dabba s, sorry, x into dx by ds plus dabba phi by dabba y dy by ds plus dabba phi by dabba z dz by ds. This is what we get. But now this dx by ds, how can I write this? So if I take this equation, x is equal to x naught plus as, so if I differentiate this, I will get it as dx by ds is equal to a. Similarly, if I do dy by ds, I will get it as b. So this dx by ds is a, this dy by ds is b, and this part is c. So I can write this equation as d phi by dx a plus d phi by dy dabba phi by dabba y times b plus dabba phi by dabba z times c. This is what we obtain. So if you see, so this equation, if I just take this equation and write it over here, so what we have written there is we have d phi by ds is equal to dabba phi by dabba x a plus dabba phi dabba y b plus dabba phi dabba z C. But this is nothing but a dot product. So I can write it as dabba phi by dabba x I cap plus j cap dabba phi by dabba y plus k cap dabba phi by dabba z, dotted with this ai cap plus bj cap plus ck cap. This is what we get. So if we dot product this, we will get this above relation. So just we are writing in terms of dot product. Now if we notice, this vector is nothing but our unit vector u. So the directional derivative d phi by ds is given as, so this is an operator. So this is written as del phi dotted with u, where this del is an operator. This triangle, this is an operator which is called as the del operator, and it is given by, sorry, this is I cap dabba by dabba x plus j cap dabba by dabba y plus k cap dabba by dabba z. So this is then very important operator. This is called as the del operator. So this is called as the del operator, or it is also called as the nabla, but we will call it as del. So this is del phi, and this del phi, it has a name. This del phi is called as the gradient. So we can also write it as grad of phi, like rather than having this as, so we can write it as grad phi or just del phi. This del is an vector. So notice that this del has this I, j and k, so it is a vector. So it is an operator. This dabba by dabba x acts as an operator which acts on some scalar field to get some vector. So this gradient, so this gradient of a scalar is like operating something on a scalar field to give you a vector. Now let us consider one example. Now let us consider a surface on which phi is constant. So let us consider one surface like this, a curved surface for instance, and let us consider a point on this surface. Let us name it as P. So we have a constant, a surface on which phi is constant, on which phi is constant. So C means constant, and U is a tangent to this surface. So let's say this goes like this. So this U is tangent to this surface at a point P, and this point P is given by the coordinates x, y naught, and this is z naught. So now what we have to do is we have to find out d phi by ds. So delta phi by delta s. Now let us consider some points on this curved surface. Let us consider this point as A. So this from point P, let us draw one line over here. So this is A, this is some point B, and say this is some point C, and it is like this. Now all these are secants. This PA, PB, PC, these are secants. Now on this surface, since phi is constant, so any change in phi will be 0. So this, the change in phi, sorry, the change in phi will be 0 because phi is constant. So it has some particular value. Consider it as an equipotential surface. So it has an equal, so it is just a number, so equal number. Say it is, say if I have an equal potential of 10 volts, so it has 10 volts everywhere. So if I take the difference of final and initial point, whatever I consider 2 points, so it will be 0, the difference between them. So if delta phi is 0, then I can say that delta phi by delta s is also 0 for any such path, for whatever the paths we take, PA, PB, PC. So any other path also, so if I extend this and say that this is another point, so this also for d phi by ds will be 0. Now, but we know from, so limit delta s tends to 0, delta phi by delta s is nothing but d phi by ds, where delta s tends to 0. Now just see, this is the s, this is the s for this line, whatever it is. This for PA, this is the S. So if I say delta S tends to 0, delta S tends to 0 means what? I'm going towards this point. So this secant, the delta in the limit delta S tends to 0, so then I'm making this line very short. So this line will go from here to here like this, like this, like this, and finally it will become a tangent. So it will be on that point P. So in the limit delta S tends to 0, so all these lines will become in the in tangent direction. So d phi by ds in the direction of u is 0. Now what does this mean? Now we know that, so this, in this limit delta s tends to 0, this d phi by ds in the direction of u is 0. Then u along tangent to this surface phi is equal to constant, means that gradient of phi is perpendicular to u. Now what does this mean? We recently have seen, just few minutes back, we have seen that the directional derivative, so if I write the directional derivative as d phi by ds, so I can write it as gradient of that scalar field dotted with u. So but d phi by ds is 0. So d phi by ds is 0 means what? This gradient of phi dotted with u is 0. Now when the dot product between them becomes 0, so we know that this a dot b, the dot product of two vectors, can be written as this modulus of a modulus of b into cosine of theta. So if theta is 90, if theta is 90 degree, then a dot b becomes 0. So the angle between the two vectors is 90, means they are perpendicular. So I can say that this gradient of phi dotted with u is 0, means this grad phi is perpendicular to u. So this has a very good physical implication that we have to see. We will study this. So this vector del phi dot u is 0. So it is perpendicular to the surface. So if I take this gradient of phi dotted with u on a surface, so if I want to, suppose if I have any curve and I want to find out some tangent, so I can find out the tangent to this one, and also we can find out the perpendicular vector, so the normal vector we can find out. So it can be asked what is the normal to this surface and etc. So we will see this, we will take these problems and make it clear. Now let us see some problems. So we have solved less problems, so let's see some very simple problems. So we have to find out the gradient of following. Now gradient, by definition we know grad phi or f, where f is the scalar, is given by I cap del by del x f plus del f by del y. So this is j cap plus k cap del f by del z. So using the same formula, so grad f of xyz will be equal to I cap del by del x into x square plus y cubed plus z raised to 4 plus j cap del by del y x square plus y cube plus z raised to 4 plus k cap del by del y of x square plus y cube plus z raised to 4. Now we have to just solve this. Now this solving this is easy. Now what we know is, so it becomes I cap. Now this is, so this is partial derivative with x, so only x gets differentiated, so this becomes 2x plus j cap, and here it becomes 3y square plus k cap, and this becomes, sorry, this is z, so this is 4z cube, where we have used the formula d by dx of x raised to n is equal to n x raised to n minus 1. So this is the answer. Let us see more problem. So again we need to find out the gradient. So gradient of this function f xyz, I am not writing it, but this is I cap dabba by dabba x into x square y cube z raised to 4 plus j cap del by del y x cube, sorry, x square y cube z raised to 4 plus k cap del by del z x square y cube z raised to 4. So if we calculate this, now these are the product. So in the product, what we differentiate, the other two remains constant. So we are differentiating this with respect to x, so y and z remains constant. We are taking the partial derivative with respect to y, so this z and x remains constant. We are taking partial derivative with z, so this two remains constant. So by doing so we get I cap, this remains, so differentiation of x square is 2x, this remains y cube z raised to 4 plus j cap x square, y is differentiated, so this becomes 3y square z to the power 4 plus k cap, so this becomes x square y cube 4 z cube. So this is what we get. So now next one, so we have this, so again we need to find out this gradient of f. So this is gradient of f of xyz, so I cap del by del x e raised to x sin y ln of z plus j cap del by del y e raised to x sin y ln of z plus k cap del by del z e raised to x sin y ln of z. So if we differentiate, same, we will keep, when we are differentiating with x, we will keep I and z constant and etc. So we get I cap. So this e raised to x, differentiation of e raised to x is just e raised to x sin y ln z plus j cap. This is I cap. So e raised to x constant, sine, differentiation of sine is cosine, ln z is constant plus k cap. So e raised to x sin y remains constant and ln of z is, so differentiation of ln z is 1 by z. So this is what we get. So for today we will continue our problem. The next video will be on the problems itself. So we will solve some more problems in some next coming videos. So thank you for joining me. Thank you. Thank you. See you all on the in the next video.